Everybody got a handout? Let's shut that door. Okay, infrared spectroscopy. Okay. Infrared spectroscopy, type of spectroscopy. You'll see different types of spectroscopy in organic chemistry, IR, NMR, mass spec, although that's really not spectroscopy, it's more spectrometry. What do we mean by spectroscopy? We're using what? Spectrum, spectroscopy. We're using light spectrum, different types of light, and different types of light interact with molecules in different ways, and we can get different information. So what type of information can we get from IR? How does a compound interact with IR light? In most cases, the compound absorbs the light, or maybe refracts it or something. And so we do this to study the molecules, because obviously we can't see the molecules. But we can see what they do to light. Let's get this thing fired up. Document camera. And on the front sheet of the handout is 2 IR spectra. Top one is of acetaminophen, bottom of caffeine. Many of you have taken or ingested these compounds. So let's first look at what an IR spectrum looks like. Pull it down to the bottom of acetaminophen. And the video is, we noticed yesterday, is a little bit not as good as the other room. And I'm not sure I can do anything about it. Hopefully it's suitable. Okay. Have spectrum. Basically all these peaks are absorbances. We have axes, this is transmittance, or basically absorbance. Okay? The more transmission you have, the less absorbance you have, but it's basically the same thing. Down here on this axis, we basically have, well, it can be of anything you want, but it's the light. It can be frequency, it can be wavelength. You can turn it into any of those. It can, essentially energy. We have equations for all that. This is wave number, if you can see that on your paper. So the wave number. So what we do here is we're scanning the IR region of light here. We hit go. In the old days, you would just do one scan. As you scan the spectrum, and the compound is like maybe sitting here, and you're shining the IR light at it. But as the frequency that you're shining changes, as you scan, then the compound all of a sudden it absorbs that frequency, and then boom, it absorbs that frequency a little bit more and broader. And then it doesn't absorb much, maybe a little, and then it comes through and it's not absorbing, it's not absorbing. It doesn't like this IR frequency, but then all of a sudden, boom, 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 it absorbs all these frequencies. So that's essentially the frequencies of absorption that takes place in the IR region. This goes from 4,000 to about 400 wave number. Wave number is in the units of reciprocal centimeters. 1/centimeter. So when we say centimeters, it sounds like we're talking about wavelength as opposed to frequency. But it's not exactly wavelength, it's 1/centimeter. Another way to write that is centimeter to -1. And another way to say that is reciprocal centimeters. That's what's actually plotted. So this is 4,000 reciprocal centimeters. We're going to talk about a little bit more of that. How you do some calculations or adjust that and maybe get frequency or something else. Now, in IR, we will learn that really each functional group gives peaks. And really each bond. What you're really seeing is the bond is absorbing the IR light. And so we also then know from experience what type of bonds absorb where. And we know that an NH and an OH absorbs in this region, which is to the, we'll say to the left. Okay? Higher wave number. We know that CHs absorb or give peaks in sort of this region here. We know that carbonyls, whether it's part of a ketone or aldehyde, usually give a pretty intense peak in this region, about 16 to 1700 reciprocal centimeters. And there'll be tables in the next couple of pages. We know that you typically get a lot of absorbance down here. These are hard to really interpret and to assign every peak. Instead, what we do call this is, from here down, is called the fingerprint region. Lots of peaks down there, and it's used just like a fingerprint for a human. Okay? Every compound will have a unique fingerprint region, a unique appearance of the peaks. You can use that, for example, you find some white powder in some bathroom on I-20 truck stop. What is it? Maybe it's cocaine. Well, take it to the lab, run an IR. You'll get an IR, you'll have a fingerprint. Sure, you can find an IR of cocaine online. Look at the two fingerprint regions. Are they the same? They are. There's a good chance it's cocaine. If they're vastly different, there's a good chance what you found is not cocaine. Okay? Use it just like a fingerprint. Of course, if you find somebody's fingerprint there, it tells you, you don't know anything about it unless you can compare it to some known. You know? If you got Al Capone's fingerprint on file, you can compare it to his. And, okay. So that's acetaminophen. By the way, what's the functional groups in acetaminophen? Amide, or carboxamide. Okay, cool name for amide. Amide, what is this here? A phenol? Yeah. Down below we have caffeine. You see that the fingerprint region is obviously very different from the one above. Okay. Once we learn more about IRs, you can look back at those in more detail. Okay. First thing we need to look at is sort of the refresher on the electromagnetic spectrum. Shown here. And we go from energy, that's the high energy in at the very top, high energy in. Gamma rays, okay, very high energy. X-rays, a little bit less energy, but still X-rays can be harmful. Of course, they can be useful for medical stuff. In terms of chemistry, what information do we get from X-rays? X-ray crystallography, okay? Of course, imaging, but more chemistry related. X-ray crystallography, a molecule will refract the X-rays as the X-ray light moves through the crystal, and the refraction pattern can be interpreted to give a structure. Closest we can come to seeing the molecule almost. It's very amazing how that can give a structure. A lot of mathematics went into that, and the guy that invented that process was about 25 when he did it. His dad was a scientist. About 25, he won Nobel Prize at like age 31. A very young guy that did all that. His name was Bragg, I believe, B-R-A-G-G. Okay, what's next? A little bit weaker, ultraviolet. What's after ultraviolet, coming to the weaker side? Visible, and invisible can be divided. Roy G. Biv, y'all familiar with that mnemonic? Red, orange, yellow. Which is the higher energy in? Red for Roy or Biv, V for violet? Violet's the higher energy in, right? I got blue listed here, but then violet here. That's because after violet, what do you get to? Ultraviolet, right? Okay. Roy G. Biv backwards. After red, what do you get to after red? Infrared. And then infrared is into the non-visible again. So infrared is weaker than visible. Ultraviolet is higher in energy than visible. That's because the UV light from the sun is actually the most harmful rather than the visible. Weaker than infrared, microwave. We use it to pop our popcorn, bake our potatoes. What else do you use it for in chemistry? What information? Microwave is not used much, but it is used to study the rotation of molecules. It's actually very minor, and you won't see it here in your mannequins. By the way, ultraviolet and visible is a combined spectroscopy called UV-Vis. Okay, we will see that a little bit in this course near the end. Infrared today, microwaves, no. Radio waves, we can listen to Rock 106. What else can you use radio waves for in terms of chemistry? Radio waves are used for NMR. Okay, NMR is covered in organic 2 here. NMR is probably the most important of the organic spectroscopy techniques. Uses radio waves. And then where do we see application of NMR in the hospital? MRI. Okay. Basically, when they do MRI on you, anybody ever had an MRI? Okay. What do they do? Put you in a magnet? Okay. Well, we got a magnet upstairs, except we don't put people in it, we put chemical compounds in it. Okay. They did an MRI on the water in your body. And it's amazing. The water in different tissues gets different responses or signals, and they turn that into an image. They actually used to call it NMR way back when, but people got afraid of the N word, which was nuclear. Okay? And so they had to take nuclear out of the name, and they changed it to MRI. They didn't change anything. It's still nuclear. Just can't tell people that they're dealing with nuclear. They get afraid of it. But everybody's got nuclei in their body, right? Okay. Infrared. So radio waves. So which are stronger? Gamma, radio waves are the weakest. Which has higher frequency? Which is high frequency in? This is here, right? High frequency goes for high energy. Which has the longest wavelengths? Radio waves. Long wavelength, shorter energy, shorter frequency. So you remember all that? Radio waves are like big as football fields, big waves. Down here we have gamma rays. Very, very high frequency. And that's a short wavelength. Okay, so what's going on when the molecule absorbs infrared light? A given molecule, caffeine. Caffeine will interact with X-rays one way. It will react with ultraviolet light in another way. How does it interact with IR? Okay. Well, really, the process involves the bonds. Okay? The bonds and the vibration of the bonds. And particularly, the one type of vibration we're going to talk about mainly, and I'll try to illustrate very simplistically, is a stretch. Okay? But a stretch is a type of vibration. And a stretch is going to have a frequency. Because a bond, while we will talk about bond lengths in class maybe, and you can see them in tables, a bond, like a carbon-carbon bond, single bond, is not just sitting there at a certain fixed bond length. It's actually doing what? It's actually vibrating by stretching in this case. But that can be at a frequency. It can vibrate slow frequency, maybe 1 per second, or it can vibrate fast, 3 or 4 per second. Okay? Different bonds vibrate or stretch at different frequencies. Now it turns out that here's a bond minding its own business, walking down the street, part of a molecule, stretching at this frequency. It turns out that if you shine electromagnetic radiation on it that matches that frequency, the bond will absorb the energy. Okay? Now you could get into the mechanics of how does it really absorb it. Basically what happens is, it's minding its own business, doing this, okay? Certain frequency. Now Myron, I want you to throw some IR light at me, which by the way happens to be the exact frequency range that is going to match this. Okay? Don't throw any ultraviolet at me because that ain't going to do anything. I'm not interested in ultraviolet. I'm interested in IR because that's the frequency that I'm basically vibrating at. Throw me some IR light. Okay? What happened? I absorbed it and I went to a higher vibrational level. Now how did I actually absorb it? Well, that's probably a lot of physics. And, okay. The idea is we go to a higher vibrational level. Do you agree that when I go from here to here, I'm at higher energy? Okay. The bond took on the energy. Because it took it on, it absorbed it. And we can plot that because we can, here's what we started with. If the bond absorbs it, then we have less and we can plot that. So that's what we're plotting if you go back to the first page. Boom, the bond absorbed it, okay? But why do we get so many peaks? That's because for a given compound, you have different types of bonds. You may have CH bonds, you may have CC. You may have bonds that have different hybridizations. Some of the carbons may be sp3, some may be sp2, and thus that changes the bond strength. Okay? For example, you're all one molecule. There's one molecule out here, but each of you is a bond. Okay? And so my molecule here has 22 bonds. I want each of you to illustrate the vibration of your bond that you are. Okay, this one over here is vibrating fast. This one's pretty slow. Okay? So here you go. I'm going to throw out some fast light. Well, she's going to absorb because she likes fast light. I need to throw you some slower light for you to absorb. But eventually, as I scan the region, I will hit all the exact frequencies that you like, and you will all absorb. And I can plot all of those absorbances. Okay? That's what's going on with the IR. And even though we talked about different, I threw you a faster frequency, I threw you a slower frequency, still everybody got IR, because this is all IR. So the one thing we need to ask at this point is, why did you vibrate faster and you vibrate slower? There's two main things that the bond stretch frequency depends on. You can find these in Hooke's law, and you'll see that in physics when you do springs. And it's the same idea. It depends on two things. Mass of the atoms that are bonded and strength of the bond. Mass of the atoms and bond strength. Now in physics, when you talk about springs, you'll talk about strength of the spring. Well, that's analogous to strength of the bond. And then you'll talk about the weight on the end of the spring. You'll put a 5-pound weight on it or whatever. Well, that's just like putting a big atom on the end. It's very analogous. And you can actually calculate, you have to have a constant, which we're not going to talk about. You can actually calculate the frequency of the vibration. And the frequency you can turn into wavelength. And then if you take the reciprocal of the wavelength, you now have a wave number that would be on that baseline. Everybody with me? Okay. So, mass of the atom, strength of the bond. And that's it. Now we can predict, relatively, where do we expect things to occur. So, let's go back. Let me ask you a question here now. Say we had have two bonds, okay? One bond over here, Andrea. You have two marbles on the end, okay? And the bond over here, Scott. You have two bowling balls or two boulders. Which one's going to vibrate faster? One with the boulders on the end or the marbles? Marbles. To move these boulders is going to move slow. Okay? Lighter atom is going to, the bond's going to vibrate faster, stretch faster. Okay? Well, let's focus on this one. If this is stretching faster, a higher frequency, it's going to want higher frequency light to match that. So it's going to absorb higher frequency light than Scott. So if you absorb higher frequency light, should your peak be more to the left or right on an IR spectrum? You seem very confident about that. Why did you say to the left? How do you know left is higher frequency?
It's 1 over.
What does it say? How do you know the left is a higher energy? What have we said about anything? What?
We know that wave number should be proportional to frequency.
Tell me again, wave number is proportional to frequency?
Yes.
Explain why.
from C equals splitter velocity or wave equals its frequency times its wavelength, so 1 over its wavelength would be the velocity times its wavelength.
Okay.
That
I thought
frequency-
I thought a frequency went up, wavelength went down. Oh, we're doing what?
Inverse.
We're doing inverse, right? What are we plotting? We're plotting inverse wavelength. 1 over centimeters. Okay? Basically, I want you to understand this, okay? I don't want to just tell you what we're doing, boom, move on, okay? Plotting inverse. So really, what you said is wave number, which is inverse, is actually proportional to frequency. Because wavelength itself is not proportional, what do you call it, reciprocal to frequency. For example, let's go back to the front. This is 400 wave number. What is this in wavelength? That's 1 over 4,000 centimeter. Wavelength equals 1 over 4,000. That's what the wavelength equals. That's a wave number. Well, let's go down here. What is this wavelength? Wavelength equals 1 over 1,000 centimeters. Which is a higher number, 1 over 4,000 or 1 over 1,000? This is a larger number. You see, it's reciprocal. This is actually a higher wavelength. Now you can do the math here. But this is a higher wavelength. What is this in terms of frequency? Higher, longer or shorter? Well, this is a longer wavelength, so it's shorter frequency. So in terms of energy, what is this? Yeah, see, this is the low energy end. This down here is the shorter wavelength, thus higher frequency, thus higher energy. So Andrew, you did get it right. But do you know why you got it right? Or was it just a good guess?
Good guess.
Okay, that's all right. So, it's a little bit of wave number, thinking of things. So, your bond has marbles. So, is your bond, we'll ask the question again, you expect your peak compared to Scott's to be more to the left or the right?
Left.
Correct, yes. Higher frequency, that's the higher frequency end. Right? That's also the shorter wavelength end. Because 1 over 4,000 is shorter than 1 over 1,000.
So when you do this, do you use a big enough sample that orientation is just like completely randomized and won't make a difference, or do you try and control the orientation of
Orientation of what?
like specific bonds? I imagine would be depending on how they're actually oriented to the incoming IR light, would absorb or not absorb.
Well, that's a great question. Never had that question. Very physical-based questions. It's good. I just wonder where you get that inclination from. It's good though. You need to meet Dr. Zuckerman. You know Dr. Zuckerman? Yeah. See, Dr. Zuckerman is peak chemist and things like that. I have to defer to him. But it's a good question. You're probably right. It may do a lot of just in the end it's a wash because all the bonds are like that. Very good fundamental physical questions. Okay. So at this point we can start looking at tables, and instead of just memorizing them, we can sort of say, hey, yeah, that makes sense. Okay? So here's the first table. It's very generic. Okay, fingerprints like 15 to 1600 here, okay? All your single bonds are going to give peaks in the fingerprint. And by the way, I'm mainly describing stretches. Okay? There's other types of vibrations. Your book will talk about bends and wiggles and rocks and all types of stuff. All the bonds, and it can be more than just 2 atoms. It can be 3 atoms that do sort of like this. All this stuff can have frequencies. And all these frequencies can match IR frequency and give affordances. Okay, in the end, single bonds are going to give peaks in the fingerprint. Except if there's an H involved, that's actually going to give a peak way on the other end down here. Your CH, OH, and NHs are going to be sort of in the 3,000, 3,500 range. The next table will be a little bit more specific. Tell me why, when there's an H involved, is it that way so much?
H is lowest.
Is it Caleb? Why?
Their molecular force.
Well, CH really isn't hydrogen bonding. What are the 2 things that affect the vibration? Mass of the atom and the bond stream. What do you know about H in terms of mass? Very light, especially compared to these others. See, these others are like nitrogen, 15 times larger than an H. Okay? Oxygen. Now, you could maybe say, well, what about helium? It's only 2 times lighter. Well, you see, the ones between 1 and 12 are not that commonly seen. H is so light, so it's like having a marble on there. That's why they're way down here. Take home is, single bond is fingerprint except for what? Except when there's an H involved. Okay? Now, if we go to double bonds, we move more to the left. Does that make sense? Which is stronger bond interatomic bonding? Single bond CC or C double bond C? Obviously double bond because it has a sigma and a pi. That's like a stronger spring. It's going to vibrate faster. Okay? Stronger springs actually do vibrate faster. Think about a slinky. That thing won't vibrate. It's so weak it won't do anything. Okay? Now we can make this even stronger. We can make a triple bond. We move more to the left, more to the high frequency. That vibrates even faster, and it requires higher energy light to match it to get it absorbed. Okay. You also have C triple bond N. Typically, you don't see a C triple bond O unless it's charged. So that's a very generic intro. The next table is more about what we're going to be using and pretty much what you need to know. There's a touch more than you need to know here, but essentially 90% of this you don't need to know. Now you don't sit down and memorize it. What you do is we eventually just learn this by using it, and before you know it you're going to say, I already know 3/4 of that, and then you kind of look at a couple others that you haven't really used much. Okay, now what we're going to do is we're going to start looking at actual IRs, and when we look at them, we'll refer back to this page. And many times I'll ask you what's here. For example, I do want to point out a couple of things. Your CHs, we did say they're going to be down here, but there's some precision here. And really at 3,000, just above 3,000 is your H's that are on an sp2 carbon. And just below 3,000 are your H's that are on an sp3 carbon. It's a magical line at 3,000. Now if the H is on an sp carbon, it's about 3,300. There's also a good amount of variation in your carbonyl placement. In general, it's about 1,650 to 1,800. But that can vary, and they're just telling you the variation there. Okay, so here's an IR. Anybody want to try to name that compound? It's got 6 carbons. It's an alkane. Hexane, yes. We'll do nomenclature a little bit later on. Hexane. Since we have structure, we can start with structure and say, okay, what type of bonds do you see? Tell me what type you see. I see CC bond, but it's single, right? Because it's single, I'm not even going to talk about hybridization because we know where's this going to give a peak in? Fingerprint. All single bonds fingerprint except those that have an H. Fingerprint, right? Where's fingerprint? It's about 15, 16 here. Ones in the fingerprint, we're not going to usually try to label or identify. Okay, non-fingerprint, we got this cluster of peaks right here. If we draw a line, it seems to be just to the right of 3,000. What is that? Yeah, we just pointed it out on the table. What is that? Yes. And what's the hybridization of the carbon? sp3CH. That's what this is here. Because look at each of these carbons. Do you agree that each carbon is sp3? Look at that carbon. How many H's on that carbon? 2 H's. So how many bonds is it making? 4. You agree that that should be tetrahedral? Yeah, it's sp3. So all of them are. All the H's are sp3CH, and so you get peaks just below 3,000. Note that just above 3,000 there's nothing there because there's no sp2CH. Okay, let's talk about quantifying. Real quick, how many H's in this compound? 14. How'd you know that?
2n plus 2.
2n plus 2. Why did you know that 2n plus 2 was the answer?
Because there's no charge.
Not really because there's no charge. Because it's an alkane, meaning it's totally saturated. There's no degrees of unsaturation in this structure. So you know 2n plus 2 is your saturated number. Yeah, it's saturated. It's a saturated hydrocarbon. So all 14 H's, okay, what you cannot do is say, okay, I expect 14 peaks. Can't do that. We can do that with NH's and OH's, but not with CH's. All we can say is we have some peaks here in this region. That means there's that in the compound. It may only be 1, or it may be tons. Okay? You can't quantify with your CH's. Where's the CC? I'm not sure. It could be this. I don't know. I'm sure you could look it up in a table and they would give you an idea. But we're not going to identify peaks in the fingerprint. Maybe 1 or 2 when we'll look down there. Okay. You guys have a leg up on the yesterday. Yesterday we hadn't covered hybridization, and so I had to kind of do a little bit of explaining hybridization. You guys should be ready to go with hybridization, yeah? What's different about this compound? First off, we'll see this later on. This is sort of condensed. Parentheses, CH2, what is that, a 2 or 3? Yeah. It's like 2 CH2s bonded to each other. And of course, it's really the carbons bonded to each other, and each carbon has 2 H's. Okay? Different ways to show compounds. But what's different here than was not in the top compound? We have the alkene, carbon-carbon double bond. And so, while this here are all sp3CH, those are all sp3 carbons, these carbons are what hybridization? These are both sp2. Now again, you see how they got this H sitting here? That H is not bonded to this carbon and that carbon. They just sort of got it condensed in there. It's really, that carbon is double bonded here, 1 bond to H, 1 bond to that carbon. Okay? You gotta always be aware of a variety of ways to show compounds. And you gotta say, oh, I know the true structure. And then this carbon is double bonded to carbon and then 2 H's. And all this is in what type of geometry? Trigonal planar, okay. But these are sp2CHs. Where do we expect bonds for that type, or peaks for that type? Remember the magical line? Look at your table. Somebody tell me the exact values from the table for sp2CH. 3150 to 3000?
Yeah.
Okay, you see it's just above 3,000 up to 3150. Do we have a peak that's above 3,000? Magical line I would draw. We got that, and what do we have here? It's actually just one peak, even though there's 3 sp2ch bonds. Again, you can't quantify. What else do we expect different from above? Fingerprints about right here. We got a CC double bond. Where does that say in the table? Stop. Alkene, about 1650. Do we have a peak at about 1650? Why, I think we do. See there? It was not in the above spectrum, was it? What is that? Now, I'll always give you this table here, and we can get the exact wave number. 1500, 1600, it looks like it's about 1640. I remember this from yesterday. It almost like 1642, is that what that is? It's almost like that's also 1642. I don't know why there's two. This number is the intensity, and the more intense, actually the lower the number, because that goes from 100 down to 0. It comes down, it's approaching 0. I don't know why, but this looks like 1642 from the table, and that is what? That's your CC alkene double bond. Rest is fingerprint. What is this peak here? Anybody give? What is that, about 1800? What is that peak? Taylor? From table, anything in the table that should be that peak there?
I see it, but I don't know what you call it.
What do you see? Those are all carbonyl compounds. Those are all carbonyl. Does this molecule have a carbonyl in it? Okay, so does that make sense?
That's its number.
Yeah, but does if that's the structure, should it? This compound doesn't have a carbonyl. So if you know that's the structure, you can't call that a carbonyl because there's no carbonyl in the structure. Could be, but I think these are all like kind of pure compounds. I think what that is an overtone. Okay. I see a strong peak here at what? About 900. What is the exact number? 910. An overtone is double that minus a touch. Double that would be 1820. Yeah. What is this peak at?
1821.
1821. Okay. It's actually double plus a touch. But it's very close. It may be experimental error. You got a little error in IR. I still think it might be. What is an overtone? An overtone is, okay, I'm minding my own business. Okay? Here. Maybe that's the CC single bond. I don't know. But they're sitting here. Okay? Then you throw some light at me. Tell me to pronounce your name again. Ecosia. Throw some IR light. I go up here. And I absorb that amount of energy. And there it is. There's the absorbance. Okay. But throw again. I really want different type of light. What I can do also is instead of going from here to here, I can go from here to there. Do a double jump. And to do a double jump, I have to absorb twice the amount of energy. Okay? And that would be where I absorb twice the amount of energy. It'd be double, it's actually minus a touch. Because as you go up, it's not exactly double. It gets a little smaller as you go up. So some bonds absorbed the energy that Nicosia threw at me. But then some of the bonds also like the double amount that maybe someone else threw at me. That's an overtone. Also, I think called a second harmonic. Is that what it's called? You know some physics?
This would sound on the end states, which basically all the energy.
You know, I think it's also called a second harmonic. Maybe in guitar strings or something. There's other places where that's seen, but I don't really know. I think it's an overtone. We'll see other overtones along the way. Okay. How about this one here? Why don't you assign peaks there? There's the structure. Structure's given. Later on, I'll give you an IR with no structure. And you'll have to just look at the peaks. And, okay. For now, structure's given. Assign what you can. Hopper, you have something assigned?
Yeah.
Shout it out.
The first one's a SPCH.
Is-
That peak.
SP what?
Carbon hydrogen.
What's the averagization?
SP.
SP. SPCH. Right here. Because here we have this alkyne, and then carbon is SP. Triple bond region, single bond region. We can envision linear, 2 pi bonds, okay, orbitals. So we have this SPCH bond, and according to the table, it gives a peak where? About 3,300,
Yeah.
okay. Do we have a peak at about 3,300? Certainly. And it's pretty intense. The exact number is what? 3,311, is that right? Probably see it.
Yeah.
Okay. Somebody else. Kendall?
This next little thing at 3,000 is SP3CH.
Just below 3,000 is SP3CH? Certainly. All these carbons here, that's condensed, what is that, 3 CH2s, and then a CH3 on the end. All those are SP3CHs. There we go. Tell me your name. Sarah?
The next week.
Next peak. We're at what value? Reciprocal. Right
About
now.
a little over 2,000.
What is that?
Would that be the triple bond?
Carbon-carbon triple bond. If you remember from the very generic table, that's sort of the triple bond region. I made a note in one of the tables, because because I think the table says 2250. What did I say in my note?
Often.
Often lower, yes.
This one's not 21.
What is that actual value?
2120, sort of.
2120. Okay, I may not write the units up there every time, but CI is usually lower. I wish they would have said 2150 in that table. It might even be a typo. Usually alkyne is not above 2200. Cyano is. Okay, Connor?
What's the number for sp3ch? Because there's a few that are right under 3,000. Can you say what the number was?
Yeah, sp3ch is just under 3000.
So what on there, which one did we?
Oh, it looks like that's 29.
2962, 2937, and 2876.
Yeah, this 27, you see that number is not that low. That means it's not that strong of a peak. That's probably those little blips up there. May or may not be part of the sp3ch. And with no structure, it's really not anything else. Sometimes in IR you get little rogue peaks that you just have to kind of ignore. The more experience you get in savviness, you say, can I ignore this? Right now we know structure. And so we know that, okay, we don't expect a peak there, so we're going to ignore it. If you didn't have structure, you couldn't be so quick at ignoring a peak. You have to say, is that an overtone, or is it really a peak? Or, and your experience will develop. Anything else to assign there? Fingerprint. We have a little blurb right there. That's kind of carbonyl region, okay? It's carbonyl region. We certainly don't have a carbonyl. Also, carbonyls are typically intense. Probably nothing. It may be overtone. I mean, that's a huge peak. Usually huge peaks, that means this really absorbs light. That's why it's so intense. If it really absorbs light, that means it's a good chance it may do a double jump. If it does a double jump, it will be double. So what's that? 6, 7, 8, 9. 6 something, the double peak would be 12 something. See, we're not even over there yet. Oh, that's all I can assign. Anything else?
So there always seems to be this extra, whenever you have the sp3ch's, this one here and all of the other ones, is that from the sp3ch's that have carbons on one, or CH3s or CH2s?
I don't think anything of it. It might just be coincidence in those. You have to see if it keeps looking like that. Okay, next compound, what do we have that's different here in this structure? We've got this is a benzene ring, an aromatics, the granddaddy of benzene rings. 600 ring with 3 pi bonds. Okay. Oh no, we skipped the bottom. What type of function group is this? Also an alkyne, but the difference is that alkyne has an H on one of the carbons. That's called a terminal alkyne. To have an H, that means it's going to be on the end. This is called an internal alkyne. There's no H. Since there's no H, we do not expect a peak where, Barbara? 3300. And indeed, you see, this one down here, there's no strong peak at 3300. So there's no SPCH. We do have a little blip up there. It certainly doesn't look like the peak above. And then we have the same old sp3ch, but there's plenty of that through there, and this guy here on the end. What about the alkyne, CC triple bond? It's there. That's it. What's the value? Somebody?
24.
2064?
54.
2054? It seems awfully low.
The next one's 26.
Somebody have the extra handouts?
So the one right above that's 2671. So
Still seems low. It's not, there's not one for 21 something?
2054 is the next one.
Wow, that's awfully low. I didn't realize it was below 21. Makes me wonder if that is indeed, yesterday we said it was the peak. The CC triple bond. The table says, well, 2250 off and lower. I wish I had a book with lots more tables. Well, we say that's it. What do we notice different from the peak above? Not position, but
It's not.
intensity. A lot weaker. Okay? Take home here is that your internal alkyne CC triple bond, the peak is a lot weaker. Sometimes it may even be absent. And what I'm wondering is it actually absent and that peak is just some row peak that happens to be close by? Question of why is it weak and absent? Well, every bond inherently has a propensity to absorb. It goes beyond mass of the atom and strength of the bond. And actually, if you look back at Hooke's law on the second page, you see how it's got that constant in there? Well, every bonding is going to have a different constant. And some have a higher constant than others. And the higher the constant, the... Okay, no, that doesn't make sense. That's going to actually change the frequency. Thought I was on this number. I don't think that works. Okay, let me go back to this. The propensity for this bond to absorb also depends on the polarity of the bond. The more polar the bond, the more eager it is to absorb. Okay? The carbon triple bond above is more polar. Now, it doesn't look like there's any polarity, but the H being so light on one end, and on the other end being carbon, there is a difference in polarity, and it also may even be weight difference. I think it's usually written as polarity. We're trying to explain that. Basically, this internal, because this is the same, it's not as polar. Because it's not as polar, it doesn't absorb as much, and that's why your peak is weaker. It can actually sometimes even be absent. See, on the other hand, a C triple bond N tends to give a stronger peak because it's inherently more polar than in this. Okay, the next page we have aromatic ring. We should have our sp3CH. That lines up pretty nicely. Let's draw our magic line here. Magic line. Looks to me like we have sp3CH on that side, and on this side we have sp2CH. Everybody agree? Does that make sense? sp3CH. And then here. With your benzene rings, hopefully it's obvious that there's one H on each carbon. Not that one. And you see that that's trigonal planar, one pi bond, that should be sp2. And so you have these sp2CHs giving peaks to the left of 3000. We also have these double bonds here in the ring. Plain alkene would be 1650. We saw that earlier. What does the table say about an aromatic CC double bond? Yeah, it's going to gives a couple of peaks at about 1600 and 1500. aromatic CC is like here and here.
Is that the same one? Would you expect to see two peaks if you only had one? Never mind, you wouldn't have just one. Okay. Because in a ring. Never mind.
Really, it's really more than just the double bond. It's probably, one of those peaks is probably coming from just a ring doing some flexing or something. You can read about it. It's really just aromatic peaks. Usually just described as the double bonding. But actually there's more structural complication here, because this is really an aromatic, it's completely delocalized.
So I guess my question, would you expect to see both a 1500 and a 1600, or would it be an handful or possibly?
Typically you get one at each, one about 15. Typically even the other. I mean, you typically get two or three peaks in this region when you have an aromatic. If you look back at a non-aromatic, you won't have sort of 2 or 3 strong peaks here. Another thing you get with an aromatic ring is sort of this mountain range at about 17, 18, 1900 through there. The mountain range. And some books that are very detailed will actually tell you what different mountain ranges mean. Where that one there looks like it's like 4 and then 1 minor one or something. There's different types of mountain ranges. Again, if you flip back at a previous one, like look at the very first one of hexane, the very first IR we looked at. You see how it's just straight across through there, there's no mountain range? Aromatic, typically, I call it an aromatic signature. So down below, first off, we see the mountain range again. You see how it's got it through here? This compound has sp2CH. Question?
On the one we just finished, around 1400, would that be considered an overtone? Because there's, on the chart we just were looking at a second ago where you moved it.
Overtone of a peak at 700?
Yeah,
Is there a strong peak at 700?
it looks like it. So that's what I was asking. Yeah, it's 699. Right at 1400 and you're right at like 700 almost.
Here, you think one of these is an overtone of this?
Yeah, the overtone,
Right.
a little bit to the right at 1400.
Here?
Yeah.
I don't know, it's pretty intense. Usually overtones aren't quite that intense.
Okay.
I don't know. I kind of doubt it. It's just a little bit too intense.
Okay.
Usually overtones are sort of little blurbs. So the one below has sp2CH. What does it not have that the one above did have?
SB3.
Yes, it does not have sp3CH, and so that's why it does not have a peak. I can draw a straight line through 3,000. Everything's above 3,000, and we can confirm that. You see, that's 13 or 19. 3,000. You see, there's nothing at 29. sp2CH, aromatic. You see this cluster of peaks in the aromatic region, CC, the ring type of stuff, and then fingerprint. Some books will tell you down here what that might mean for an aromatic. Y'all want to take a short break, or y'all want to plow through and say we keep on going? I think we're in pretty good shape. We can plow on through it. I'll go over the rest of these IRs. Next ones looks like alcohol and ether, and then there'll be a couple of amines, and then we'll move on to the carbonyl compounds.
So we're skipping the mineral P light that was that doing with the last one. CO.
We did that one, didn't we? Aryl chloride?
Oh, okay, I didn't know that. So we did that line too.
Which one are you looking for? The CCL? Where would you expect that to absorb?
CL should be,
But it's a single bond,
so it'd be the fingerprint.
fingerprint. CCL's fingerprint. All single bonds fingerprint unless it has an H. Looking at the IR, what do you see here that's different from the others? Got a big absorbance over here. What is this? That's your OH. Remember, single bonds or fingerprints have OHs, NHs, CHs. CHs are around 3,000 or the 3,300. OHs and NHs are 32 to 3,500. And OHs, textbook, very broad and intense. But a word of caution. On the newer instruments, like we have upstairs, the OHs are not as intense. Peaks down here are not as intense on the newer instruments. Okay? Why is that? Originally, when you did an IR, and by the way, there's photos of IRs in your lab manual. We have 2 different IRs. The instructions for both are in there. If I was teaching the lab, I would expect you to read the instructions and use the instruments yourself. Okay? Not sure what Dr. Idell expects. But in the old days, the IR light, there was a generator of the light, and then there was a receiver. Okay? The sample you set in between, so the light shined through the sample, and the absorbance took place, and then there was detectors. And you had to actually make a film. The compound was in a transparent film, so the light could shine through it. It took a little bit of effort to do that. Nowadays, the instrument just has a little eye sitting right on top of a little kind of a shelf. It's a diamond eye, and the light comes up from the bottom. You don't see any of this, and it reflects off. Okay, because it just reflects off, the absorbance on this end, it turns out, is not as intense as it used to be. So you're probably not going to see an OH this intense upstairs. What else do we have here? Yeah. The trade-off is now you just put a little bit up there and goop. It's a lot faster to run an IR now. What do we have here? sp3CH. What else is in our molecule? I see one other bond. What other bond is there that we haven't talked about? CO. Okay? Obviously that C is bonded there. These H's are here. CO. Where's the CO? Single bond. Fingerprint, right? Okay. Right there. That's all we're going to assign. I'll come back to the CO. I was going to try to point it out, but it almost looks like it's not there. I'll come back. And below, we might point it out. What's the functional group below? It's an oxygen bonded to 2 plain carbons. It's an ether. Okay. sp3CH, plenty of that. What else is in the compound? CC single bond, fingerprint. CO single bond, fingerprint. Obviously there's no OH, so you don't see a big peak. I do see a little blip right there. Not sure what that might be. An overtone would have to come from a peak in this region. I think it might be, anybody have a guess what that might be? This is an actual IR.
Would be an interaction between the O.
Oh, what?
An interaction between the O and the H's within the molecule.
Well, those H's are on carbons. You're not going to get any hydrogen bonding there. No. I think that's probably a little water. I think this is probably an actual IR. Could be a little water. An impurity. Water has OHs. Okay? A note about water. A lot of times when you're in the lab, you make a compound. Maybe it was recrystallized from ethanol water mixture. You run the IR. You see a peak over here when you shouldn't. What could it be? It could be water. Maybe it's not dry yet. You let it dry some more. Rerun the IR. Okay. Okay. One time to look in the fingerprint is your CO single bond. The peak down there is pretty strong, and it's about 10 to 1200. Do you see a strong peak, 10 to 1200? That's one time to look down there and sort of confirm. I was trying to look above, and I really didn't see it for the alcohol up there. You really see that with esters, and we'll point that out later. Okay, next one is, what's the functional group? And amine, A-M-I-N-E. Primary, secondary, tertiary. Primary, because it has one carbon attached, nitrogen. Down here in the OH-NH region, you see two peaks. That's for your two NH bonds. So we're actually quantifying. Okay. But, minor point here, it's not two individual NH bonds giving two peaks. It's actually a three-bond system. Here's an H, and I'm the N. You get one peak when they're all stretching like this. You get another peak when they're doing like this. A symmetric stretch and an asymmetric stretch. That's why you get two peaks. But in the end, two NHs give two peaks. While one NH is going to give just one peak. sp3CH, and the rest is pretty much fingerprint. And the compound below is what type of an amine? Not primary, but secondary, because it's the nitrogen is bonded to two carbons. And so there's only one NH. Of course, see that H is like that. It's really not like that, right? And there's a lone pair there. One NH, see it over there. This one is, for some reason, a little broad. That could be some hydrogen bonding that broadens the peak. Well, it looks like a little cow udder. Okay? Comes down to a point there. That's your NH peak. And then what do we got here? Okay, sp3CH, and the rest fingerprint. And what type of an amine is that? Tertiary amine, how many NH peaks you expect? Obviously no NH peak, and there's none there. We do have the sp3CH. I mean, you can't even tell the nitrogen's in the compound from the IR. The one below is another secondary amine. Happens to be, what do you call an amine bonded to an aromatic like this? Aniline. Happens to be an aniline. The name of this is N-methyl-aniline. Okay? And nitrogen is sp2 hybridization, right? It really didn't affect anything here. There's one NH, see the NH? I can talk about this though today. You see how that NH is stronger than the previous ones? If the nitrogen is conjugated, and what we're really talking about is the lone pair. If the lone pair is conjugated, the NH typically is stronger. Does everybody agree that this lone pair is conjugated? What does that mean? That lone pair is in a p orbital. Why is it in a p orbital? Because next door, there's a p orbital. What's the hybridization of that nitrogen? sp2. We talked about that this morning. That's the exception. That's conjugated. Conjugation makes the peak stronger for some reason. Probably because it makes it more polar. And then I'd have to explain that a little bit. We have other things there. 3,000, we have peaks on both sides. Okay? Don't we seem to have, I can draw a straight line. Don't we seem to have peaks on both sides? So we got sp3ch. Where's that? That's just out here. And then all these H's are on sp2 carbons. A little bit of mountain range. It's not very much, but it's certainly something there. And then you got your sort of CC aromatic, 15, 1600. Okay, we made it to the carbonyl compounds. How are we doing? IR look pretty doable? Okay. When we end, we'll see the types of problems that are in the lab manual, or the workbook. That's the types of problems you see on the test. You may also see some short answer or multiple choice questions. Okay, what functional group do we have here? Yeah, it has a carbonyl, but the functional group is called a ketone. Where does carbonyl give a peak at in the IR? 1650 to 1800. Okay, this is sort of carbonyl region right here. And there you go. And the exact value is, what's that, 17, 18? Very middle of the road carbonyl. And then what else do we have in this here? We have our sp3ch. We also have carbon-carbon single bond, but that's fingerprint. Ah, what is this over here?
Overtone.
Carbonyls often give overtone. What's double this? 34, 36? Okay, 34, 36 minus a touch. What is this peak? 34, 16? You see how it's double minus a touch? And carbonyl is sitting there minding its business. It absorbed, but some of the carbonyls absorbed twice the energy and went way up here. And that's where it absorbed twice the energy. Because there's certainly no OH or NH, although it could be enol, and I'll just throw that out there for our big video here. Okay. I've always called it a overtone. Organic 2, we'll see enols. Actually, we'll see enols in organic 1 during test 3. ENOL. What's the functional group below? Aldehyde. Carbonyl, right here. What's the value? It's almost 17, 18 again, isn't it? No, that's just coincidence. We have peaks here, sp3ch. Any other types of CH in this compound? sp3. What type of CH is this? What's the hybridization of that right there? Is it Blake? What's hybridization of carbon? sp2. That's an sp2ch. Where do you expect that to give a peak? Typically. But look at the table. This is an aldehyde sp2ch, and the table will tell you a little bit something else. Aldehyde sp2ch.
We have 30 to 2700.
What does it say, 1 or 2 peaks? To me, it's usually 2 peaks at about 2750, 2850. That's what I would tell you. The table may be slightly different. Do we have two peaks at about 2750, 2850? Two, right here and here. That one's sort of buried. Usually when we do our SP3, there's not something like over there at 2750. It's usually like right there. The sp2ch of an aldehyde is unique. It's actually here. Let's see. Why? What does that tell us about bond strength? So there's no change in CH here versus CH here. It's still the same masses. What about bond strength? The fact that it's more to the right, what does it tell us about the bond strength? It's weaker. That could be evidence that it's weaker. Then we could say, well, why would it be weaker?
Because of the dipole of the carbonyl group.
Perhaps. Why would that make it weaker?
More polar, that's stronger.
Certainly if this was carbon, then that would not be a carbonyl, and we would expect that to be 3000. So it seems like it has to be something with the oxygen.
It's taking the electrons from, pulling the electrons from.
The electrons being pulled from this bond into here, weakening the bond. I don't know. The main point I'm trying to get at is we can use the way the peak moved to maybe say, hey, it looks like for some reason maybe the bond has gotten weaker. Right? Certainly the mass of the atoms haven't changed. I'll tell you something about this. You guys tend to always forget this CH peaks here. Always. What's next functional group? What is this here? Ester. Anybody ever watched Sanford and Son? Just me and Scott? Anybody else? Anybody ever heard of Sanford and Son? Okay. When I was growing up, it was Sanford and Son and a Braves game. Or maybe Andy Griffith in a Braves game. Okay. What was Lamont's aunt's name?
Esther.
Esther. Okay, thank you. Y'all check it out. Esther. Aunt Esther. Got a carbonyl here, right? Where's this big guy? Actual is 1743. It's actually a little higher than the others, yeah? Esters tend to be a touch higher. Can't put much into that, but okay. What we got here? Everything else is saturated, right? When I say saturated, I'm saying sp3ch. Okay? The rest is saturated. Probably an overtone. Carbonyls often give overtone, especially in textbooks. Not so much these days because things down here tend to be weaker and you don't see overtones as much. What's this big peak here at about 1200? Remember I told you you can look down here sometimes? This is the CO single bond. One time you can look down there and sort of confirm Esther. That's sort of your ace in the hole, your like last resort. What is this here? Functional group? Amide, amide, amide. The long name would be carboxamide.
You skipped the bottom one.
What?
You skipped the bottom one on that last page.
What was it? Was it another ester? It was just an aromatic ester. Let's skip it. Okay. I mean, at this point, we can sort of just plow on through and finish them up. We've seen most everything here. There's a couple of new things about the carbonyls. Carbonyl here, what do we see about this carbonyl position?
It's not,
What's the position?
1639.
15, 16, looks like
49.
1640,
1639.
1639? What is that compared to the others?
Lower.
Lower.
Yes, amides give low carbonyls. I don't want to get into why. We may a little bit later, definitely in organic 2. But it has to do with conjugation, because that lone pair is conjugated with the carbonyl. Okay, the orbital. See that pi bond there, double bond? Well, this is also here. Now, if that's an oxygen, it would also be conjugated. But see, oxygen is more greedy. It doesn't like to share its electrons. Nitrogen is a good sharer. And it's pumping electrons into this, and it's actually weakening that bond. When you weaken the bond, you move this way. Take-home message, amides have low carbonyl. Okay, we can discuss more why. Two NHs. One thing about this one is your CHs tend to be, for some reason, fairly weak. You see a little bit sort of under here. I can't see if that's to the left or the right. Yesterday, I think we said that was to the left, and then we were wondering why come there's nothing to the right, because we do have sp3CH.
There is one that looks like the 28 or 3.
That little blip,
I guess.
that's almost too far to the right to be CH. I would like to see something right at the edge. So in the end, it's a little bit atypical. It's almost like it was run upstairs, where everything is a lot weaker. Okay, the amide below. Now, top amide's primary because it has one carbon attached to nitrogen. The bottom amide is secondary. 2 carbons attached. That's only one NH, and you see the NH peak. The NH is pretty intense because the nitrogen is conjugated with the carbonyl. We said earlier, if the nitrogen is conjugated, the NHs will be more intense. This one, I think, you see, you've got peaks on both sides. Because we have both sp3CH and then the sp2CH is around the ring. Tertiary amide, no NH, so there's no NH. What is that over there? Certainly not a strong NH like we saw before. It might be a little water. And then we have our line there. Because this compound does have both sp3CH and sp2CH, and then a low carbonyl. That carbonyl is probably 1620. 1626 or something?
Yeah.
Pretty low carbonyl. That's not the lowest you'll ever see. There's another amide below. I say we move ahead. It's just a primary amide. There's no sp2CH, so everything is to the right of 3000 here. The carbonyl is split. Sometimes carbonyls and amides can be split. I wouldn't worry about it for you guys. The reason why, wouldn't worry about it. Let's get to this. Anybody know this functional group?
That's from this.
Acid chloride. or known as an acyl chloride. Got a carbonyl. Here it is. What do you notice about the position, though?
Pretty high.
Pretty high. I don't know if
15, 16, 17.
1802.
1802.
Yeah, the exact number is 1802, is that right?
Mhm.
Is that high or low?
High.
High carbonyl. Acid chlorides give high carbonyls. If you look in the table, it probably tells you that.
I just wanted to ask in the SI, is there any reason why we only do acid chlorides as opposed to acid bromides or iodides?
Well, these are very reactive. They're not that stable. And so they're usually just reactive intermediates. And so everybody just knows chlorides. It's just the most common. Sometimes acid fluorides have unique uses. You rarely see acid bromides. It's just kind of like nobody makes them. You just, the bigger the halogen, the more expensive it is. This does the job. Everything else is saturated. Okay, sp3CH, probably an overtone over here. The one below is aromatic, or it has an aromatic ring, and so you see a little more activity through here in the 15, 1600. The mountain range is pretty much not that much there, though. You do have peaks on both sides of 3000 because you do have the sp2 now. I think we've got just a couple more to go here. What functional group do we have here? Carboxylic acid. It's your main acidic functional group for organic. What does the table say about the OH of a carboxylic acid? Very broad and strong. So you see a very broad and strong peak. You see how it's flat, very broad and strong. And it goes not just at 3400, but it goes down in like 2600, all through there. Of course, that's the classical. Could be weaker, especially upstairs. sp3CH sort of being obscured, you know. This could be it here on the bottom. It's trying to give some peaks there at the bottom of that absorbance. Carbonyl. Carbonyl is pretty standard, 16, 17, 10 or so. Not sure why it has a little ridge. Wouldn't worry about that ridge.
Is a CO bond? Would either of those be a CO
You could
bond?
possibly say that's the CO.
Oh,
Usually it's like about 11 to 12. That's more like closer to 13,
that could possibly.
possibly. One below, I'm not going to write anything on the board, but well, I see some broadness over there, but it's certainly not as intense as the one above. So you see some broad there. Structure is not shown. Carbonyl. The structure, I think, has an aromatic ring with sp2CH, but it also has some sp3CH. So sort of both sides. So here and here, sort of trying to get some peaks. At the same time, it's doing the broadness. The broadness is due to extensive hydrogen bonding. Carboxylic acids. We talked about hydrogen bonding this morning. The H of one molecule interacting with the O of another molecule. I think that's kind of where we ended at. We'll say more about that as the first thing tomorrow. So that was the carbonyl groups. We have another functional group, the CN, the nitrile, or the cyano group. Where does it give a peak at? Triple bond region, 2200? Yeah, 2200, 2250. And so that's it right here. You see there's really no carbonyl. What are these peaks here? Your aromatic CC. Mountain range up there. Actually, there's mountain range all kind of all the way across. And then this is up what, above 3,000? That's your sp2ch. The one below is sort of miscellaneous. I used to say something about it. I'm not going to say anything right now. Just have a carbonyl. Carbonyl is actually a little lower than most ketones. That's because it's conjugated on both sides. This is a little weak up here. This molecule does not have sp3ch. All of the H's are sp2ch. So that those peaks, little cluster of peaks, should be going above 3,000. Okay, two things to show. One, I want to show you a little bit of example from the research lab, and then I'll show you some problems in the workbook that you'll see on the test. Okay. Look at this compound here. We made these compounds. I got a hole punched. These compounds here were made for then doing something with that. The next step was to have the nitrogen displace the bromine, have the nitrogen bonded to the carbon instead of the bromine. Okay? With the goal of making a new ring. This is an IR of the starting material. It has an NH2. Does it look like an NH2? Yeah. You can try to interpret some of the rest, but there's your NH2. When we did the reaction, one of the first things we do when we get a new product is we run and get an IR. And when we did the reaction, of course, after doing some research and getting it to work, that's the desired product with the nitrogen now bonded to the ring instead of the bromine. Does this IR look like the product? Could it be? Now there's only one NH. Okay? Sometimes we did this reaction, we do IR, and there's two NHs, and it's like, looks like still starting material. It didn't do anything. IR is real quick and easy to run. It's okay, we have compounds. And if you look at the fingerprints, they're certainly different too. Okay. Let's take a look at the workbook. Any questions about IR? Three. Yeah, what time we get out of lab? 5? Okay, we got plenty of time. Okay. Page spectroscopies all together. Spec 33. That's the first one. Starts on 33. This is sort of, you will see something like this on test. Compounds at the top, choice of compounds, and the idea is to assign each spectrum a compound. Not all the compounds will be used. Let's actually look at a different, yesterday we did 33. Well, let's do the same page, but let's do this. Instead of, yesterday we did A, 1 and 2. Today let's do 3 and 4. You guys on the right over there do 3A. You guys do 4A on this side. So find the compound that goes with that spectrum. And then we'll see how you did. Well, C3A is probably one of the easiest one on the whole collection. Have you ever got it figured out? Hopefully, yes. Because the spectrum 3A, we actually just looked at 3 minutes ago. And I wish I'd have given you a number. So what is 3A? What do you see? What kind of peaks do you see? I can't pull it down and show the compounds. What do you see here? I see a big peak in this region, which is what? You got it right there, right? CN? All right? Taylor? And what is this here? sp2ch, and then the CN. See, the reason I think it's pretty easy is there's only one choice up there that has a CN. You see that? Okay. Did you think this was something else? Did you think it was maybe a CC triple bond? Well, if you think about that, if you said it was a CC triple bond, then what's the answer? There are none. So this is a little test-taking just strategy, right? Do you guys see why 3A is the nitrile on the aromatic ring? Okay. And it's actually the same exact spectrum that we just looked at for the compound. How about 4A? So 3A was what?
H.
Is it H over there? Okay, H. And the one on the bottom you're saying is what? F is in Fred?
Yes. We do amide.
Tertiary amide
Mm-hmm.
with both sp2 and sp3ch?
In the aromatic ring.
Aromatic ring, let's see. Okay, magic line. It looks like it's both SP2CH and SP3CH.
The nitrogen wouldn't show up on this since it doesn't have any NH. It's tertiary, it wouldn't show up on here.
Yeah, does this really look like a
There's no
NH or OH?
peaks.
It looks like an overtone.
It almost looks like water. That's just not. So you could maybe write something like this: OH, NH. You know, just kind of question it at this point. Okay, what else do we see?
There's
Low
no-
carbonyl.
Yeah.
How do you know that's a carbonyl and not something else? Well, it's a little broad. What's the peak position?
16, 20, yeah, 16,
16,
33.
33. Could that be a carbonyl?
Yeah,
Yeah. Broad like that?
and it's low. Which is
It's
an
low,
amide,
so that suggests what?
And it's an amide.
CO of an amide? Certainly not acid chloride, that's a high carbonyl.
And then you have all the peaks. You have
A
an
little bit of
aromatic-
mountain range, peaks in here, looks aromatic. We also have SP2CH. That doesn't mean it's aromatic, but aromatic would have that. So it looks like we have a compound that has both types of CH in terms of SP3 and SP2. Amide, but this is like, okay, is that an NH or not? Well, let's look at the choices because we're not doing this blindly. We have choices. So why is it not A?
It's not a carbon.
I don't see a broad OH. I also, that would be a standard carbonyl, 1710.
Mhm.
Why is it not B? Well, that doesn't have SP2CH. That also would be a standard carbonyl.
And there will be aromatic rings.
What about C? Well, that doesn't have any SP2CH, and that'd be a high carbonyl. What about E?
There's no S.
That's an amide. Okay. Well, is that really an NH? It doesn't look like one. Why? What's another reason it's not this?
No SP2.
Our compound has SP2CH. I don't see any SP2CH there. Ah, this has SP2CH, SP3. It's an amide. Tertiary, meaning no NH, and we say that, I think this is probably not really a peak over here.
It has a low carboxyl.
Because we certainly don't have something that matches all this and that. Everybody agree that, I mean, it's one below, that really doesn't look like a peak? It's sort of just some broadness that I've described in water. And amide at H is seriously intense. F. Fred. I mean, G doesn't have SP2CH. G would also have two carbonyls. G is called an anhydride. It's not on your functional group list. You'll see it in organic 2. It's not D because D doesn't have SP2CH.
For G, isn't that the two carbonyl groups? Would there be two peaks in the carbonyl region?
Yeah.
Okay.
Anhydrades give two carbonyls. I covered that in organic 2. So there's about 5 sheets there for practice, Michael. You'll see this. Again, you may also see some short answer on the choice, something related to the theory. Questions about anything from lecture this morning? Y'all want to get out of lab early today?
Now, is there anything we would expect different from I think you might have covered that, the SP2 NH versus the SP3 NH?
I mean, the SP2 NH is going to be probably stronger because it's going to
As far as peak intensity, I guess.
be SP2 NH probably stronger, but peak position, they're both NHs. SP2 NH is stronger, like in your amides and your anilines. Yeah, let's get out of lab early today.